Right. So the independence thing gets to be kind of a pain. So when you're taking small samples from a large population without replacement, it is reasonable to assume in most cases independence of the events. As a rule of thumb, if the sample size is less than 5% of the population size, we treat the events as independent. Okay, so what are they talking about here? Well, let's just look at this. You buy a huge 25-pound bag of plain M&Ms. That's the kind of thing you got to order from the supplier. They're huge, huge bags, almost like garbage bags full. So you draw one sample, one M&M from the bag. How much does your selection affect what's left? Not much at all, right? So even though you're drawing an M&M and affecting what's, affecting. I never do that right. Affecting? No, it's affecting, sorry. Affecting what's left in the bag, it's by so small an amount that we can just ignore it. They do this with polling all the time. So let me write it up here. Polling 1,000. They usually do, like, let's say they do 1,100. So 1,100 people for Gallup or CNN or Fox News or whatever. NPR, pick something, right? I'm just going to out of 300 million people. Is it possible that your calls are affecting somebody out of the 300 million? Sure. But it's not going to be a great effect. So you're just going to ignore it. And that's basically what this blue box is telling you. Just don't care, right? So suppose you go to Vegas. By the way, this is not how they do the tournament pokers, but if you're just playing at a regular table in Vegas and the dealer has a chute of pre-dealt containing 8 decks of cards. 8 decks, that's a lot of cards. What's the probability that your first 2 cards are both aces? So for this case, because there's 8 decks, you getting 1 card is not really affecting greatly what's left in there. I know it's kind of crazy, but true. So we would just say probability of ace is equal to, okay, so what's the chances of you getting an ace? There's 8 decks there, so you just say 8 times 4, which is 32 out of 52 times 8. I have to figure out what that is. Oopsie, equals 52 times 8, 416. So, okay, 32 times 32 out of 416. Okay, we're not going to bother with the whole 31 out of 416 because getting 1 card is really, really small, right? 0.0024. So you're not drawing enough out to actually have it really be affecting what's left. Now, if you're dealt a whole hand, that's a different story. But 1 card is only 0.002%, or so 0.2%, 0.2% of deck, which is smaller than 5%, so we're just going to treat it like it's independent, even though it actually isn't, right? So if you were going to treat it like it wasn't independent, you'd make it 31 out of 415. But if you're going to treat it like it is dependent, you can leave it independent, so you're going to leave it 32 out of 416. Doesn't really greatly affect this problem, but they just want you to see that in general, when you're talking about small samples from large populations, particularly this sample right here, right? That one is where it becomes really important in chapter 6 and 8. Then you're just going to ignore the fact that you drew without replacement. All right, so that's the end of that concept stuff. Now we just got to do this last problem here, which is a really important example to see. It's talking about HIV in America. Well, actually, any place, a rare disease. And this doesn't have to be HIV. I'm just using HIV because it's a pretty rare disease in the U.S. So suppose HIV infects 1 out of every 1,000 people in a population, and suppose there is a good but not perfect test for this disease. If a person has a disease, the test comes out back positive 99% of the time. On the other hand, the test also produces some false positives. About 2% of the uninfected patients also test positive. Okay, so we're going to have to figure out here how many are in each group. I'll do that, and I'll see you back after the break.